This is lecture 4, part 1 for the system development process, engineering and design of large-scale systems. And this is for IE4399, Introduction to Systems Engineering, and IE5397, System Thinking and Analysis. So in this lecture, we are going to go back to the discussion we had in lecture 3. We're going to go back to the system life cycle, and we are going to spend more time in each one of the phases, the stages of the system life cycle model. And we are going to also talk about other evolutionary characteristics of the development process and also the engineering method, the systems engineering method. So the material we're going to discuss today is part of chapter 4 of your textbook for this class. So you can read that chapter on your own. So the discussion is based on that information. The agenda for today is the system engineering through the system life cycle. We're going to go back to the system life cycle model, and we are going to talk in detail about each one of the phases and stages of the system life cycle. We're going to talk about the evolutionary characteristics of the system development process, and also we're going to discuss the systems engineering method. So let's start with the system engineering through the system life cycle model. So this lecture is devoted to describing the basic system development process and how systems engineering is applied at each step of this process. A typical major system development exhibits the following characteristics. We know it has to be a complex effort and needs to meet an important user need. It is usually requires several years to complete. It is made up of many interrelated tasks, involves several different disciplines, usually performed by several organizations, and it has a specific schedule and budget. The system development must be conducted in a step-by-step manner in which the success of each step is demonstrated and the basis for the next one validated before a decision is made to proceed to the next step. Okay, so we talk about different system lifecycle models, if you remember from one of our previous lectures. So now we're going to talk about those in detail. So let's talk about the system lifecycle. The term system lifecycle is commonly used to refer to the stepwise evolution of new system from concept through development and onto production operation and ultimate disposal. The role of systems engineering changes accordingly. The system engineering lifecycle is based on 3 different sources. We mentioned this already: the Department of Defense Acquisition Management Model, the International Model ISO, and the National Society of Professional Engineers NSPE model. So the DoD Acquisition Management Model is displayed here as an example in this figure. And this is tailored toward managing large, complex system development efforts where reviews and decisions are needed at key events throughout the life cycle. So you can see in the figure that there are different shapes representing different things. So if you look at the shape of a diamond, that is representing a decision point. We have a triangle representing a milestone review. And we had the dotted line diamond, which represents a decision point if PDR is not conducted before milestone. PDR is a preliminary design review. So this system lifecycle, the DoD acquisition management model, is tailored toward managing large, complex system development efforts where reviews and decisions are needed at key events throughout the life cycle. The major reviews are referred to as milestones and are given letter designations, A, B, C. So you can identify those triangles in the figure. So for example, A is representing a milestone review from material solution analysis to technology development. So for example, at milestone A, a requirements document needs to be approved by military oversight committee before a program will be allowed to transition to the next phase. The international ISO 15288 model, the basic model is divided into 6 stages and 25 primary processes. The processes are intended to represent a menu of activities that may need to be accomplished within the basic stages. The ISO standard purposely does not align the stages and processes. The 6 basic stages are concept, development, production, utilization, support, and retirement. And then finally, the professional engineering model is tailored to the development of commercial systems. This model is mainly directed to the development of new products, usually resulting from technological advantages or advances. So these are technology-driven developments. It is also partitioned into 6 stages. So we start with conceptual, technical feasibility, development, commercial validation and production preparation, full-scale production, and finally, product support. The systems engineering lifecycle model. So this is the one that I mentioned in the previous lecture that you needed to memorize. This is the one that is a combination of the 3 that we just presented. And this is the one that we're going to use for this class. So your project is going to be following this systems engineering lifecycle model. And as you can see here, we have the 3 stages with 3 phases in the first, the concept development, 3 phases in the engineering development, and then 2 phases in the post-development. So the first, the concept development stage, which is the initial stage of the formulation and definition of the system concept perceived to best satisfy a valid need. Okay, so this is what you're trying to do, or what you're going to try to accomplish with your project. We're going to identify a need, which is what you did in your proposal. Now we're going to start defining a concept for that system that is going to be able to, a perception of a concept that, or a development of a concept that could solve that valid need, and then we're going to define that concept. The engineering development covers the transition of the system concept into a validated physical system design, meeting the operational cost and schedule requirements. And the post-development includes the production, deployment, operation, and support of the system throughout its useful life. So the concept development stage, which is the first stage here, the concept development stage. In the concept development stage, analysis and planning that is necessary to establish the need for a new system, the feasibility of its realization, and the specific system architecture perceived to best satisfy the user needs. The principal objectives of the concept development stage are to establish that there is a valid need for a new system that is technically and economically feasible. Number 2 is to explore potential system concepts and formulate and validate a set of system performance requirements. Number 3 is to select the most attractive system concept, define its functional characteristics, and develop a detailed plan for subsequent stages of engineering, production, and operational deployment. Number 4 is to develop any new technology called for by the selected system concept and to validate its capability to meet requirements. The level of effort during this stage is generally much smaller than in subsequent stages. the subsequent stages, the next stage will be the engineering development stage. The process of engineering the system to perform the functions specified in the system concept in a physical embodiment that can be produced economically and maintained and operated successfully in its operational environment. System engineering is primarily concerned with guiding the engineering development and design, defining and managing the interfaces, developing test plans. As you can see, if you remember from our case studies, test plans are very important. If you don't do the right test, you might face very challenging situations. So developing those test plans is part of the systems engineering primary task. Determining how discrepancies in system performance uncovered during test and evaluation should be best rectified. The main bulk of the engineering effort is carried out during this stage. In the engineering development stage, the principal objectives of the engineering development stage are perform the development of a prototype system, satisfying the requirements of performance, reliability, maintainability, and safety, and to engineer the system for economical production and use, and to demonstrate its operational suitability. And then we got to the last part, which is the post-development stage. These are activities beyond the system development period, require significant support from systems engineering, especially when unanticipated problems require urgent resolution and encounter. So in this figure, figure 4.3, it shows the principal stages in the system lifecycle. These are the three stages that we just discussed: concept development, engineering development, and post-development. And the arrows represent the input outputs for each one of these stages. So the development stages of a new commercial aircraft. So this is an example. Consider the evolution of a new passenger aircraft. We're going to list a minimum of 5 events, actions that will occur during each stage of the systems engineering lifecycle model. So starting with the concept development stage, this will include the recognition of a market for a new aircraft, the exploration of possible configurations, such as number, size, and location of the engines, body dimensions, wing platform, and so on, leading to the selection of the optimum configuration from the standpoint of production, cost, overall efficiency, passenger comfort, and other operational objectives. The above decisions will be based largely on analysis, simulation, and functional designs, which collectively will constitute justifications for selecting the chosen approach. So that's for the concept development stage. For the engineering development stage of the aircraft, life cycle begins with the acceptance of the proposed system concept. So as I have mentioned in class already, in the concept development stage, you will have multiple designs, but at the end, you have to decide on which one it will be the best in meeting the requirements of the customer, and also be more efficient in terms of cost, schedule, and performance. So the system, the engineering development stage of the aircraft lifecycle begins with the acceptance of the proposed system concepts and a decision by the aircraft company to proceed with its engineering. The engineering effort will be directed to validating the use of any improving technology, implementing the system functional design into hardware and software components, and demonstrating that the engineering system meets the user needs. This will involve building prototype components, integrating them into an operating system, and evaluating it in a realistic operational environment. And then the post-development stage includes the acquisition of production tooling and test equipment, production of the new aircraft, customizing it to fit requirements of different customers, supporting regular operations, fixing any faults discovered during the use, and periodically overhauling and replacing engines, landing gear, and other highly stressed components. So let's look at each one of the stages separately. We're going to start with the concept development stage. This encompasses 3 phases: the needs analysis, the concept exploration, and the concept definition, as illustrated in figure 4.4. This will be the first stage. The 3 phases are listed in figure 4.4. So in the needs analysis phase, we define the needs for a new system. It addresses the questions: is there a valid need for this new system? And is there a practical approach to satisfying such a need? The output of this phase is a description of the capabilities and operational effectiveness needed in the new system. From there, we move to the concept exploration phase, which examines potential system concepts. It addresses the questions: what performance is required of the new system to meet the perceived need? So for instance, what temperature should these systems operate? Is there at least one feasible approach to achieving such performance and affordable cost? The output of this phase includes our first official set of requirements, typically known as the system performance requirements. And we're going to spend some time after spring break discussing the set of requirements and how to define requirements. In addition to an initial set of requirements, this phase produces a set of candidate system concepts. The concept definitions phase selects the preferred concepts. It addresses the questions: what are the key characteristics of a system concept that will achieve the most beneficial balance between capability, operational life, and cost? The output of this phase is 2 perspectives on the same system: a set of functional specifications that describe what the system must do and how well, and a selected system concept. The next stage is the engineering development stage. It also encompasses 3 phases: advanced development, engineering design, and integration and evaluation. And figure 4.5 illustrates the 3 different phases of this engineering development stage. The first phase is the advanced development phase, and it has 2 primary purposes: the identification and reduction of development risk, and the development of system design specifications. This phase is especially important when the system concept involves advanced technology not previously used in a similar application. Systems engineering is central to the decisions of what needs to be validated and how, and to the interpretation of the results. The engineering design phase, the detailed engineering design of the system is performed during this phase. The system engineer is responsible for ensuring that the engineering design of the individual components faithfully implements the functional and compatibility requirements. The task of this phase deals with converting the component specifications into a set of component designs. The integration and evaluation phase, the output of this phase are twofold: the specification to guide the manufacturing of the system, typically called the system production specifications, and the production system itself. The latter includes everything necessary to manufacture and assemble the system and may include a prototype system. The third stage is the post-development stage. And it's split into 2. The first one in 2 phases. The first phase will be the production phase. No matter how effectively the system design has been engineered for production, problems will arise during the production process. For example, a strike at vendor's plant, unanticipated tooling difficulties, bugs in critical software programs, and so on. Such situations threaten costly disruptions in the production schedule and requires prompt and decisive remedial action. Systems engineers are often the only persons qualified to diagnose the source of the problem and to find an effective solution. Operational and support phase. Proper planning for the operational phase includes provision of a logistic support system and training programs for operators and maintenance personnel. This planning should have a major participation from systems engineering. There are always unanticipated problems that arise after the system becomes operational that must be recognized and included in the logistic and training system. Very often, the instrumentation required for training and maintenance is itself a major component of the system to be delivered. Okay, so in this lecture, we went through the system engineering lifecycle model. We are going to continue this discussion in our next lecture, and we're going to also talk about the systems engineering method.